Well, hopefully you've watched my video that explains how this circuit works. This circuit's known as a bridge rectifier, and it's used to convert AC signals into DC. Now, the DC you get ends up being a sort of choppy form of a DC signal, but still, it converts AC to DC in this manner. A generator's always changing its polarity from positive to negative. So let's say positive polarity sends current momentarily clockwise through the circuit, and when the polarity changes to negative, it sends the current counterclockwise. Because of the behavior of these diodes, then the current can only flow to the right. When the current's going clockwise, it takes this path and continues on and makes its way around the circuit. When the current goes counterclockwise, it takes this path and makes its way all the way around. So regardless, the current can only go to the right through this resistor. Without the bridge rectifier in place, if a generator sends current directly through a resistor, then we know that current is going to alternate sinusoidally. The graph of current versus time would look like this, and we ask, what's the average value? Well, it's equal to 0. There's just as much positive as there is negative. But with the rectified circuit, the current doesn't graph like this. The current looks like this. So in other words, instead of saying I equals I maximum sine omega t, we get I is equal to the absolute value of I max sine omega t. So all the negatives get turned into positives. So let's figure out what the average value is for this graph. Meaning, how about we do this? Let's find the area under the curve. Well, I think maybe before I suggested we find the area under the curve all the way up to 2 pi for a full cycle. But I say let's just find the area under the curve for half a cycle. In other words, from 0 to pi. And then we'll ask ourselves, is there another graph that maintains a steady amount of current up to a value of pi so that the area is still the same? So what would that be here? We'll just call it x. In other words, x times pi has to equal this area. Okay, so let's figure out what this area is. Well, that's just the integral of sine theta, right? How about this? Instead of calling it t, let's call it omega t, so that it's theta. So we have a graph of sine theta, and we're going to divide it up into little slices. We're going to integrate to find the area, which means every one of these slices is just a rectangle with a width of d theta and a height equal to sine of theta. So all we're doing is finding the area of a rectangle with a height of sine theta and a width of d theta and adding it all up. So that's what we mean when we say we're taking the integral of sine theta d theta, and we're going from 0 to pi. So the integral of sine of theta is negative cosine. So you get negative cosine theta evaluated from 0 to pi, which gives us cosine of 0 minus cosine of pi, which gives us 1 minus negative 1, which is 2. Okay, so there we have it. X times pi has to equal 2, so x has to equal 2 over pi. There you have it. If we look at a graph of sine of theta versus theta, and we find a way to turn the negatives into positives, and then we say what steady value represents the average value for that rectified circuit, then all we're saying is let's work our way up to a value of pi. And how can we make it so that this shaded area here matches all of of this shaded area. Well, that would only be the case. We know, first of all, the maximum value of sine of theta is 1, and then we found out this steady value would have to be 2 over pi. Or, better yet, instead of a graph of just sine of theta, what if we had a graph of I times sine of theta, or I times sine of omega t versus t? What is this rectified average value of I? The rectified average value is equal to 2 over pi times the maximum value. If we say I equals I max sine omega t, then the rectified average value is 2 over pi times the maximum value. 2 over pi is the same thing as about 64%. So there you have it. Rectified average value is about 64% of maximum value. Oh, somehow I already have that stated again here. Got ahead of myself. Let me delete that. Oh, I see. Okay. Well, that's one way to express the average value of AC electricity. The other way isn't RAV, it's RMS. Instead of rectified average value, it's root mean square value. So another way we can get rid of the negatives, instead of making a graph of sine of theta versus theta, let's make a graph of sine squared. So a graph of sine of theta might look like this. The graph of sine squared then looks like this. And we'll just take the same approach. We're going to ask the question, what steady value produces the same area over time? So let's go for half a cycle. Let's go from 0 to pi. So again, we're going to have to say x times pi is equal to this shaded area. So what is that area? This time it's the integral of sine squared theta d theta from 0 to pi. I always have a hard time with this one. I've got to try to remember how I can make a substitution based off the double angle formula. You probably know better than I do. Can I replace sine squared theta with 1/2 of 1 minus cosine of 2 theta? I think I've got the right trig identity there. We'll see. Okay, so this becomes the integral of 1/2 d theta from 0 to pi minus 1/2 the integral of cosine 2 theta d theta from 0 to pi. Well, this part's easy. This just gives us pi over 2. Then we get minus 1/2. Let's see. The integral of cosine of 2 theta is it's 1/2 sine of 2 theta. Now if I evaluate that from 0 to pi, this is the sine of 2 pi minus the sine of 0. Well, wait a minute. Sine of 2 pi is 0. Sine of 0 is 0. Well, this whole term is 0. Oh, so that's it. The area is pi over 2. Okay. So x times pi has to equal pi over 2. So x is equal to 1/2. But wait a minute. Wait just a minute. This is the average value of sine squared. And so that doesn't really give me the average value that I'm looking for. I need to take the square root of that, right? This is just, well, so far we've just found the mean value of our function squared. We need to take the square root of that to get us back to what we're looking for. So x RMS is equal to the square root of 1/2, which I believe is equal to 0.707. So if we have a graph of current versus time, where current is equal to some maximum value times sine of omega t, then there's a value of I RMS that's equal to, either we can say 1 over rad 2 I max, or we can say I RMS is equal to roughly 71% of I max, 0.707. Okay, and just to remind you what we showed earlier, RAV, rectified average value, would be more like 64% of I max. So the standard in US electrical circuits is referred to RMS value, okay? I think we'll use that as our way of saying an average as opposed to rectified average value. So what's that mean? What are the outlets in our house giving us? Those are a source of AC electricity. So your standard outlet looks something like this. If you look at it carefully, you'll notice that one of the prongs is a little bit longer and the one on the right's a little bit shorter, and they have the ground plug. The left is a little bit longer, the right is a little bit shorter, and they have the ground plug. So what type of voltage do we have here? We often refer to these as 120 volt outlets. So if we make a graph of the EMF that's available versus time, is that it? Is it a graph of sine, or is it a graph of cosine? Or shoot, maybe it's a graph of negative sine. Well, the truth is, none of that matters. Like we've said earlier, what if you were to adjust your origin in time? If I take a graph of, that says EMF is EMF maximum times sine omega t, and I shift my time axis here, so I no longer say t equals 0 at this point, I say t equals 0 here, then my graph of sine just became a graph of cosine, and so on and so forth. So that doesn't really matter so much. Anyhow, here's what I'm getting at. What's the peak value then in all these graphs? Is that what we mean when we say it's 120? Positive 120 to negative 120? Well, no. The RMS value of the voltage is 120 volts. Yeah, for a standard outlet, the RMS voltage of a standard outlet is 120. So what's the maximum? What's the peak voltage in this graph? Well, if we just found that I RMS is equal to 1 over rad 2 I max, then that means I maximum is equal to rad 2 times I RMS. So we can call it maximum, or we can call it the peak value. The peak value of the current from a household outlet is the square root of 2 times 120. Grab a calculator, let's check what that is. About 170. In fact, it goes something like this. The longer of the two prongs pretty much hovers at 0 volts. They call that the neutral wire. So if we make a graph of its EMF versus time, it might float a little bit above 0, but should be very nearly 0 volts. The other wire is referred to as the hot. And if we were to graph the electric potential of the hot, that's the one that's oscillating, and it's oscillating from positive 170 to negative 170. And of course, the other prong is true ground. So if we make a graph of that one's voltage versus time, that one really is just strictly 0. We'll explain more about this in the next video on transmission of electricity, but for now at least we've established some relationships between RMS values and maximum values.